Hello again, time for physics. This is video lecture 23.1, where we are going to discuss in this chapter a new result for us known as Gauss's law, named after a 19th century mathematician slash physicist, Carl Friedrich Gauss, who made a lot of contributions to physics and mathematical physics. And this is one of them. It's the topic of an entire chapter. And we're going to develop the ideas that we need to state Gauss's law, and then practice and practice until we start to understand it. Let me give you the big picture of what we get from it. Why bother learning this new content known as Gauss's law? Here's the big picture. With Gauss's law, it turns out we are in essence kind of rewriting Coulomb's law in such a way that calculating electric fields that calculation is very, very easy if the charges that are producing the electric field have lots of symmetry to them. Very symmetric shapes, the most symmetric shape, of course, being a sphere. So when you have a distribution of charge that is shaped in a way that is highly symmetric, and you want to calculate the electric field that that charge produces, Gauss's law is going to be the way we're going to do it. And it is so much easier than the technique in chapter 22 that eventually I want to get you to the point where you appreciate that. But I haven't even said anything in words of what the Gauss's law says. Here's my first rough statement of it. just a kind of loose language way of saying it. Gauss's law. The amount of piercing of electric field vectors through any closed mathematical surface is proportional to the total charge inside that surface. So, a surface is something that, well, can be purely mathematical, an idea in our heads, not something that you could actually touch. Or it could be a surface that you could actually touch. An example of that kind of scenario would be a balloon that somebody has blown up and tied off so that there's air trapped inside. And then you've got that stretched membrane, that stretched surface of the balloon that is a mathematical surface. You can touch it. But it's a physical surface too, right? You can touch it. So the surface of a balloon that's been blown up and tied off is what's called a closed surface. And with any closed surface, there is an interior volume that is inside the surface that you can't get to without piercing the surface. And of course, everything outside is an exterior volume. A closed surface divides off some interior volume, kind of like protects it. Again, a blown up balloon, the surface of it would be an example of a closed surface. But sometimes the closed surface we're talking about might have a balloon type shape, like a sphere, but is a completely mental construct. We are imagining a spherical surface, okay, without there actually being one there. That's important to note, that it can be a purely mental construct. So what Gauss's law is saying is that it's going to give us a way to quantify the amount of piercing of electric field vectors through the closed mathematical surface. And that measure we're going to talk about for the amount of piercing turns out to be, in essence, determined by the total charge that's inside that surface. So the amount of piercing of electric field vectors through a closed mathematical surface is giving us information about what's hidden inside, i.e. how much charge is inside. Now, as I said, this closed mathematical surface is a mental construct. It can be any shape we choose, as long as it has no openings. It's got to be closed off so that whatever is inside is protected, and that from the outside you can't get to it without piercing through the surface. Now, such a surface is called, for historical reasons, a Gaussian surface. And of course, we're going to struggle with ways to represent that Gaussian surface in drawings, because we're drawing on a two-dimensional surface, but a Gaussian surface, being a closed mathematical surface, will have to reside in three-dimensional space. So it's always tricky to try to draw it. In fact, you might as well start to get used to how we're going to have to deal with that. The picture on the left here is a typical way that textbooks will try to represent the kind of scenario we're talking about in this chapter. So here in the middle is a charged particle. It's got some amount of charge Q. I don't really care right now what it is, except I will say, let's assume it's positive charge. We already know from chapter 22 that any positive charge, by virtue of that charge being there, creates electric field vectors throughout all of space, and that they point radially away from the charge. So what they've done in this picture is they've imagined enclosing that charge in a spherical surface, like the surface of a spherically shaped, blown-up balloon, with the charge at the center. And they're drawing that surface, they're calling it a Gaussian surface, right there. Okay? They drew it as a kind of a dashed line. And it looks now like I've drawn like a circle, but it's just a two-dimensional slice through what is actually a balloon-type shape, a sphere. And then they show some electric field vectors with rather odd coloring to the arrows. I don't quite understand that. Okay? But they show some electric field vectors at piercing the surface, the Gaussian surface, in various locations. And as we know, the electric field vectors produced by a positively charged point particle just point radially outward. So those green arrows I just drew all represent electric field vectors that are piercing that surface and pointing outward. So we clearly have piercing of the Gaussian surface by electric field vectors. We're going to want to quantify that, okay? All right. So first, let's talk about how we're going to do that. And it turns out there's a name for quantifying the piercing of a surface by a vector field. Okay, so let's get to that idea. It's called flux. Now that's an old-fashioned word, I know. F-L-U-X. And it is kind of an old-fashioned word for flow. Okay? But you'll see why I say flow in a minute. So what I want to talk about now is chapter 23, section 1, which is entitled Electric Flux. But I want to step back and be a little more general than that. So I really want to talk about the flux of a vector field through a surface. It could be any kind of vector field through any shaped mathematical surface. The general description of the flux of a vector field through a surface, very general, is the rate of flow of the vector field through the area of the surface. So I want to try to start this by being as concrete as possible, and not as abstract as it could be, so that you can visualize the ideas. So what I've drawn here on the right is a top-down view, looking down from above, on what is part of, let's say, just a gentle stream of water flowing from left to right, right? Streaming water all through that area, coming in from the left and flowing off to the right. And it's uniformly flowing water. At any given point in the stream, the water has a velocity vector v arrow, and at any given point, like here, that velocity vector v arrow is exactly the same as any other point. I'm trying to draw those red arrows exactly the same, okay? Same magnitude, same direction. We have what's called a uniform vector field. It's a velocity field, right? At every point in the stream, there is a certain velocity in meters per second. All right, and into this stream of water, I'm going to insert a mathematical surface. And so that you can visualize it, what I did is I constructed kind of a frame for that mathematical surface. I just took an index card and cut out the middle part of the paper so that what I have is a rectangular shaped frame with a hollow interior. Okay? Now imagine that hollow interior is, that's our surface. It's a mental construct because there's nothing for me to actually touch. Okay? But imagine a surface there. I could imagine a little soap film there if I inserted this thing in soap liquid and then lifted it up. There would be a soap film there. Then you could touch it. It'd break, but you could do that. But I'm just imagining a surface that's in this frame. And now imagine that I insert this frame straight down, well, vertically down, into the flowing water. So that the flowing water can go through this hole. Okay? Now this frame has some area A that it encloses, and it's through that area that the water can flow. And I can control what angle I hold this frame relative to the flow direction. I can hold it so that the flow can go right through easily, or I could rotate it so that it's edge on and the flow is going actually right around it. Okay? But I'm immersing this frame vertically down into the flowing water. And if I do that and look from above, the frame looks like a line. That's this line right there that I just drew in black. But what you're really doing is looking down from above on the top of this frame. And I'm drawing the frame kind of at a bit of an angle relative to the flow of the water. It's also very handy to mark a direction that's perpendicular to the surface of this frame. And that's this dashed line right here. And that direction is perpendicular to this surface right here. And remember, another word for perpendicular is normal. Remember normal force, perpendicular? Okay? So you'll often see that line I've drawn there dashed, also called the normal to the surface. It just means a line that's perpendicular to the surface. All right, I have drawn only for the point right at the very center of the surface, but that's enough to see the velocity vector for the water. Okay? The water flow is directly left to right, but my frame's angled a bit. In fact, it's very important to denote this angle here, right here, theta, which is the angle between the velocity vector of the water and the perpendicular or normal to the surface. Now, once I've done that, I can draw a component triangle for the velocity. Well, I can break it down into two components. One component parallel to the normal direction, and one component perpendicular to the normal direction. So let me draw them. There's the component of the velocity that's parallel to what we call the normal. And there's the component that's perpendicular to the normal. Now, if what I want to measure is the rate of flow of the water through the surface here, I contend that it's this component right there of the velocity that's the important one. Right? The component of the velocity that is perpendicular to the plane of the surface, the loop it's called. Right? The component that is along the perpendicular direction. The other component of the velocity is parallel to the surface, and that just represents the effect of some part of it skimming parallel to the surface. That's not piercing going through. So it's only the component of the velocity that is along that perpendicular dashed line, the perpendicular component. And given the v and the theta, it's not hard to write down an expression for that perpendicular component. It's right there. Magnitude v times the cosine of what that angle theta is. So then, to get the flux of the vector field through the planar area with area A. Here's the definition and the symbol. The symbol for the flux, this case is a velocity flux, is a capital Greek letter phi, and then I add a V subscript to denote that the flux, the vector field I'm calculating the flux for, is a velocity field. That's what this symbol is right there. And the velocity flux through this rectangular loop is defined to be 3 lines. Take the component of the velocity along the perpendicular direction, magnitude v cosine theta, and then just multiply by the area inside the loop. That's this area inside here. Because the bigger the area, right, the more water can flow through. So it's got to depend on that. But and the faster the water is moving, the more that can go through. So it's got to depend on v magnitude. But it also depends on the angle that this surface inside this loop makes relative to v. Okay? And that's where the cosine theta comes in. So just to try to be even more clear, I'll draw over here to the side. What if I were to hold the surface, let me try to do better than that, so that it is like that relative to the water flow? Or to say it another way, the normal is like that, which is exactly the same direction as the velocity of the flow. Okay? Then you're holding the loop exactly like so that the water can go, all the water velocity is going straight through. And that's got to give you the biggest flux. And that, of course, corresponds to theta equals 0. And over there in the cosine theta, that's the biggest, then cosine can be, it's 1. Conversely, what if I hold the loop so that it is kind of edge on to the water? The water is coming at it edge on. The perpendicular direction is that way. But the water flow, the velocity direction, is still to the right. Now the angle theta is exactly 90 degrees. And in the flux formula, I take the cosine of 90, I get 0. There is no flux in that case because the water is just skimming along the surface, not piercing, going through. And I can have anything for theta actually between 0 and 180. Okay? That can also happen. That would correspond, let me draw an angle bigger than 90. What if I rotated the loop starting here all the way around to here and then even further still, to there. But the normal was that way. And then the velocity is that way. Now the angle theta is that, which is bigger than 90. Note when you take the cosine of that, you're going to get a negative number. Yes, you can have negative flux. It just means that angle there is bigger than 90. Let's talk more about that. Velocity flux. That's the most straightforward one to visualize because you literally would have something flowing through this surface. Okay? Happens to be water. Okay? All right, it turns out it's useful when you're talking about this concept of flux to kind of extend the concept of area of a surface and think of it as a vector. So I'm going to define now an area vector, A arrow, for this planar loop. So here we are again looking down from above. There's the loop. There's the velocity vector drawn at the center of the loop. There's that normal, the dashed line, that perpendicular. Okay? All right, and now I've added what we're going to call an area vector, A arrow. Here's how we define it. First, its magnitude. That's easy. The magnitude of A arrow is just the area inside the loop. What is this area? The direction of A arrow is perpendicular to the plane of the loop. That's why I drew it along that dashed line. right? And for a flat surface like this, there's just that one area vector representing the entire area in a direction along that perpendicular. If we think of A as a vector, then my expression on the previous slide for velocity flux actually is equivalent to a dot product of the vector field, in this case velocity, with the area vector, V dot A. That's going to be very important. I can think of the velocity flux for a uniform velocity field in a planar, flat area as that dot product, V dot A, because you would then calculate that by taking the magnitude of V times the magnitude of A times the cosine of the angle between V and A when they're drawn with a common tail, which is exactly that theta that we've been using. And then this expression right here is exactly the same as this one right up here. Okay? All right, so let's now think of it. Velocity flux for a uniform velocity field through a flat area as V dot A. Okay, so this is for velocity flux, whoops, pardon me, with a uniform velocity in a planar flat area, like this one would be. Let's think about the SI unit for a minute of velocity flux. It's got to be the unit of velocity, meters per second, times the unit of area, meters squared. But that's actually meter cubed per second. Oh, well, that gives me an easy way to think of velocity flux. It's the volume of water, right, meters cubed, flowing through the surface per second. Volume of flow per second, if it's a velocity flux. All right? All right, so what I want to do now is practice with using this expression. So I'm still a little bit limiting myself. Uniform velocity field, and my surface is said to be planar, flat, as opposed to if it were bent, okay? And I want to practice with that a little bit. Let me get myself some space here so I can do some writing. And I'm going to go back and forth between this screen and a Wiley Plus animation now. So let's go to that. And now you're looking at an attempt to give you a 3D representation of a velocity field, a uniform velocity field. That's all those blue arrows that you see. You also see 3 axes, x, y, and z. Note that the velocity then is in the y direction. And then there's a planar area shaded in light blue. And there's a vector there. You see it in black labeled n hat. That's called a normal unit vector. It's perpendicular to the surface. And then the red arrow, V arrow, represents one of the velocity vectors for the water, the velocity vector right there at the origin. We just draw that one. We only need to see one because they're all the same. Okay? All right, I want to do some analysis of this. But first I want to show you what will happen if I pull the slider. There's a little slider up there, just so you can see it, that will rotate the surface about the z-axis. When I rotate it, you'll see I'm rotating the surface, not affecting the flow of the water. You'll see that the velocity vectors aren't changed, but the surface itself will rotate about z, and the n hat will rotate so as to stay perpendicular to the surface. So let me start rotating it now. It's going around like so. Right now I've gone 90 degrees roughly from where I was. Now notice that the water is hitting it edge on. So how much flux would we be getting through the surface, through the purplish area, the bluish area? None, right? In fact, there's a plot, do you see it, of the velocity flux as a function of the angle theta between n hat and v. And you can see that it's now down to 0. And I can keep going with this n hat. Now I'm going around towards the back. Notice the velocity flux curve is going negative. And you don't really need to go beyond 180. There we are. Okay, and there's that graph of the velocity flux in meters cubed per second as a function of the angle theta. Right now that theta is basically 180 degrees, whereas there it's 0 degrees. All right, I'm going to give you some information, then we're going to do some calculations together. All right, so referring now to this animation, the area of the loop, I'm just going to tell you, 2 square meters, okay? All right, here's what I want us to do first. I want us to use the graph to find the velocity vector for this flowing water. I'm going to use the graph. I will help you see that by moving and rotating the surface again. So you see the graph? See it changing? All right. I'm going to go towards the theta equals 0 limit because I want you to see what value the flux has there. Do you see what it's approaching as I go to theta equals 0? Okay. So what we see is that for theta equals 0, what you see right there, the velocity flux value, did you see, was 10 meters cubed per second, and that's a maximum. So let me now show you, back on my screen, what I'm just saying. For theta equals 0, you want to find V. The velocity flux is 10 meters cubed per second, and that's the maximum it can be. I contend we can use that, along with the formula highlighted right there for velocity flux, to find V magnitude, yes? So, phi sub V is magnitude V, magnitude area, cosine theta. I'm going to use 0 degrees there. Then the phi I'm going to use is 10 meters cubed per second, and I'm just going to solve for V magnitude. Of course, I know that cosine of 0 is 1, so I don't need to write that anymore. So V magnitude is phi sub V, the velocity flux value, the maximum, right, velocity flux value, divided by the area inside the loop. That's 10 meters cubed per second over 2 meters squared. That's 5 meters per second. Now I'm asked to find V arrow, right? The velocity vector. That's the magnitude. How do I account for the direction? Look at the animation. Look at the red arrow for the V there at the center of the square, or any of the blue arrows that represent other V's. Which way do they all point? Plus Y, don't they? So when we write that down now, for our V arrow, we have 5 meters per second, J hat. That's the velocity vector for this fluid flow, water flow. All right, now what I want to do, using that, I want to find the velocity flux through our loop if the angle theta between the normal and the velocity is 30 degrees. Okay, you want to think a moment about how to do that? Maybe even try it. Feel free to pause the video. It's good practice. I'm going to calculate it. Okay, so I hope you tried. It's good practice. Phi sub V equals, from the dot product, magnitude V, magnitude A, cosine theta. Just plug in all those numbers. The magnitude of V we just found. That doesn't change, 5 meters per second. The area, 2 square meters. And then I'm taking the cosine of 30 degrees. Right? That's what I'm told to do. So that's a 10 times cosine 30. That's, if I give you 3 sig figs, about 8.66 meters cubed per second will flow through. Less than the maximum velocity flux of 10 meters cubed per second, but still pretty good. Let's see if we can show that. So let's just try to approximate 30 degrees. Something roughly about like that. Okay? I can even rotate this thing so you can see it more from the top. See the angle between the n hat and the v? It's roughly 30 degrees. And yes, there's there's water flowing through that area. It's just not the maximum amount. And it looks like on the y-axis that the value is indeed somewhere around the 8-ish value. And of course, what we calculated is 8.66. All right. Now I want to do another one. I want to find phi sub v if the angle between n hat, or the area vector, same thing, and v is 135 degrees. You try it. Pause the video, try it on your calculator. It's good practice, and then let's see what we get. Okay, so again, we're going to do magnitude v, magnitude a, cosine theta, 5 meters per second, 2 meters squared. Now I'm taking the cosine of 130 degrees, and the cosine of an angle bigger than 90 is a negative value. So you get, to 3 sig figs, negative 0.07 meters cubed per second. Yes, it can be negative. It just means the angle between the n hat, or the area vector, and the v is greater than 90. If we look at it on Wiley Plus, 135 degrees is roughly something like that. Okay, so the angle between the n hat and the v is bigger than 90. And notice the flux value is indeed negative, and it does look like it's roughly around negative 7 meters cubed per second. So if I call the side where the n hat is kind of the front of the surface, then I see that the water is going from front to back instead of from back to front, which is the way it would be if the angle is more like that. Okay, so you can have negative flux. It will happen if the theta between your n hat and your v, or your area vector and your v, is greater than 90. Okay, so with velocity flux, now we go back to, we really do have physical substance flowing through a surface, water in this case. But you don't have to limit this whole thinking to the velocity field of an actual flowing fluid. You can take any vector field, represented by arrows, of course, and you can take any surface, and you can do this same kind of calculation to see how much piercing of the surface there is by the vectors. So, for this chapter, the quantity we're going to be interested in is the flux of the electrostatic field through a surface. Okay? The flux of the electrostatic field. So not a velocity field, but the electrostatic field. So is there something actually physically flowing now through a surface? No. But I can have electric field vectors piercing the surface. The first case, just to get warmed up, is a uniform electrostatic field and a flat or planar surface, which is just the kind of situation I was dealing with the water and the velocity flux. And we wrote velocity flux in such a case as v dot a arrow, because I defined something called an area vector for the surface. Well, now we do the same thing, except it's electric flux. So I write it as capital Phi subscript capital E. That's what that is. Subscript is telling you what kind of vector field is doing the piercing. And we just take E dot A arrow, not V, E, E dot A arrow. And then you're finding the electric flux of a uniform electric field through a flat surface. What's the SI unit of electric flux? It's the unit of electric field, Newton per Coulomb, times the unit of area, meter squared. So Newton times meter squared per Coulomb. All right, now, that's all fine, but I'm limited with that to two special restrictions. The vector field has to be uniform, meaning it's the same vector value at every point in space where the surface is, and the surface has to be flat, planar. We need to generalize that. We need to allow for a surface that is curved and for a vector field that is different at different points in space. Okay, so it's a bit of a leap, but let's look at the picture shown on the right. Now this is meant to show what they're calling a Gaussian surface, and it's this rather orangish shaped object that kind of looks like a heart on its side. Do you see that? I always thought it did. It looks like a heart on its side. And since we just were recently in Valentine's Day, why not? Let's think of it that. It's a heart-shaped closed surface, almost like a heart-shaped box of candy, for example. And it has been immersed within an external electric field, E arrow. And that direction of that field is represented by all those field lines. Do you see them there drawn in blue with arrows on them? And the electric field lines seem to point roughly from left to right. They're not quite uniformly spaced if you look very carefully. They're quite tightly spaced over here on the left side, but they're a little bit more farther spaced on the right. That tells me the field is not quite uniform and that it's getting a little bit weaker as you go to the right. Now, these field lines, some of them clearly pierce that Gaussian heart-shaped surface. So we are going to have to worry about an electric flux through that surface. How the heck do we calculate it is the point. Here comes calculus. Because here's what you do. You imagine breaking up the surface, the whole thing all around it, into a very large number of very tiny little pieces, sometimes called patches. Okay? And if you look very carefully at the picture, you can see there's a kind of a grid drawn on the heart-shaped Gaussian surface. That's representing all these little patches. Okay? Each little patch has some amount of area. We'll call it delta A. But I'm going to think of each little patch as having an area vector. Okay? Delta A arrow, where the magnitude of delta A is the size of the area of that patch, and the direction of delta A arrow is perpendicular to that patch, pointing outward from the surface. So they have highlighted in this drawing 3 particular patches to look at and zoomed in on them. So let's start with patch number 1, which has been zoomed in and shown right here. Okay? Now, there, the little patch is kind of angled down and to the left, and the perpendicular to it is going up this way. So that's the direction of the delta A arrow for that little patch. Now the electric field vector right there happens to be piercing that patch pointing inward. Oh, let me choose a different color. Okay. Like that. And so the angle between the delta A and the E, the theta, is greater than 90. But what we would do is calculate the electric flux through just that patch, okay? Through patch 1 by doing the electric field there at patch 1, E1 dot delta A1. I ought to denote it delta A1 and E1 because that's the electric field at patch 1 and the area vector for patch 1. Okay, and so that would still mean that I do magnitude of E1, magnitude of delta A1, cosine of the angle between the E1 and the delta A1. And because that's greater than 90, this is going to end up being a negative value. But that's the contribution to the flux from that one little patch. Now let's look at another patch they highlighted. It happens to be down here, in the kind of in the bottom edge of the heart-shaped surface. And now here's the blown up version of it. It's kind of down at the bottom of the heart-shaped surface. So the delta A for that patch has got to be perpendicular to the surface and pointing outward from it. And that makes it end up being roughly like that, delta A2. But the electric field vector right there just happens to be skimming along the surface, okay? So when we calculate the electric flux through patch 2, we're going to take E2 dot delta A2, that's the magnitude of E2, times the magnitude of delta A2, times the cosine of the angle between them, but if it's kind of hard to see, but there's a little right angle drawn in the diagram right there, telling me that the angle between E2 and delta A2 is indeed exactly 90 degrees, and the cosine of 90 is 0. You don't get any flux through a surface where the electric field skims along it. One more patch, the patch marked over here, 3. See it on this end? And then here's the zoomed in version right there. What's the delta A arrow for that little patch? Well, it's perpendicular and outward, so that's roughly like that. And the electric field vector there happens to be going in this direction, E3. And then we find the electric flux through patch 3 by doing E3 dot delta A3. E3 delta A3 cosine theta. And they're trying to show you here, in this case, that the angle theta between the delta A and the E is less than 90, which means the cosine of theta is positive. So that patch has a positive flux through it. So some patches, like patch 1, could have a negative flux. Some patches, like patch 2, have no flux. And some patches, like patch 3, have positive flux. So then the total electric flux is what you get when you add up over all the patches the fluxes through each one. The EI dot delta AI, but then you got to pass to the limit as the area of each little patch, delta A, approaches 0. Well, approaches 0, so the delta A's become dA's, little infinitesimal area vectors. And then you have an integral. It's called a surface integral. And we put a little circle on it to denote that it is a closed surface integral. That's what that little circle means. And inside that integral symbol, we have E dot dA. That's still just a fancy way to denote what I wrote right here. Take the E dot dA's for all the little patches and add them up to get the total. Okay? All right, so I want to give you some practice that you can answer class engagement on Blackboard. With electric flux. Because we just have to practice, right? That's probably a new idea for everybody. All right, this figure here shows what's called a Gaussian cube. It's just called that because they chose their Gaussian surface to be shaped like a cube of face area A. That means all 6 faces have area A. And this cube is immersed in a uniform electric field that has the positive direction of the z-axis. Do you see their axes they've drawn? Make them bigger so that you can see them. This is x to the right, y up in the plane of the screen, and then drawing z like this means it's coming out of the screen towards you. And they draw the electric field, one of them here, meaning all the electric field vectors point in the plus z direction. In terms of magnitude E and area A, we are to find the flux through various faces of the cube. I'm going to do part A with you, and then you on Blackboard can answer B through F. Okay? All right, let's find an expression for the electric flux through the front face of the Gaussian cube. That front face is sitting exactly in the xy plane. All right, let's use unit vector notation. For the electric field, E arrow is simply E magnitude k hat. It's a uniform electric field pointing in the plus E direction. Now here's the next question. On the front face of this Gaussian cube, what is the area vector? Now you could imagine a bunch of little dA's, but since it's a uniform field and a flat surface, I can just do a whole A vector for the whole front face. Right here, that whole area on that front face. Okay? What's the A vector for that part of the cube? You see how to think about that? Notice it's got to be perpendicular to that surface, pointing outward away from the surface. So the A vector has got to be in the Z direction, right? Perpendicular to that flat face and outward. So this A arrow is A times k hat. Then the electric flux to that front face, phi sub E, since it's a uniform electric field and a flat surface, you can just do E dot A. So that's E times k hat dot A times k hat, which is E times A times k hat dot k hat. Unit vector, any unit vector dotted into itself gives 1. So this is just positive E times A. That's the expression for the electric flux through that front face. Okay? That would be the answer for part A. Okay, now using similar kind of notation, you need to calculate the electric flux through the rear face, the face that you can't actually see here, exactly opposite to the front one that we just did. Then for the top face, well, that would be this one right here. Then the electric flux through the right face. That would be this one right here. Then the electric flux through the left face. That would be the one opposite the right one. And then finally, the electric flux through all 6 faces together, the whole cube. Okay? And that's what you answer on Blackboard. Now, I just want to do one more brief thing before I stop. I want to state for you Gauss's law. Okay? All right, so the way I'm going to do that is I'm just going to write it down right here. Okay? I'm going into section 2 briefly because of time constraints coming up into the future. So I'm now writing about section 2, where we're going to state Gauss's law. Okay? So let's state it. The total electric flux, right, just like we've been practicing with, through a closed surface, that's important, a closed surface, is proportional to the total charge inside the surface. Okay? The total electric flux through a closed surface is proportional to the total charge inside the surface. So, phi electric is proportional to, we're going to denote the total charge inside the closed surface, QENC. ENC stands for the word enclosed. Okay? All right, so the first thing we have to figure out is what is that proportionality constant? I can't just say proportional. If I'm going to actually do quantitative calculations using this new law we're stating, I need a formula that says phi electric equals some constant, I'll label it for now C times Q enclosed, and we've got to find what that constant is. Okay? All right, the way we're going to do that is look at a case we already know pretty well, a single point charge. And we're going to surround it by a spherical Gaussian surface. And then we'll be able to figure out what that constant is. And that constant will be generally correct for, and be used in Gauss's law for any situation. That's going to be the game plan. So I wanted to kind of give you a heads up that that's what we'll be starting with on the next video. Okay? But that's all for right now.